All right. Hello, everyone. Welcome to our next webinar on on-site detention for development applications. We'll just give it one more minute to bring the slides. All right. All right, so that's the screen share. Perfect. All right, so we'll quickly get started here. It's a list of things we'll cover today. Just a quick overview why we need on-site detention, the different flow estimation and parameters we need for calculations. Then we'll run through a few of the common storage estimation methods in the industry, give you a brief overview, and then we're going to close it off with some storage types, and at the end, give us a quick list of questions. You can put it in the chat in the webinar Q&A section as well. All right, so why is OSD a development condition? So what happens with developments is you have let's say a greenfield site, something like that, and currently you have existing drainage infrastructure, like a main pipe down the road. Let's say you've got a couple of developed car parks down here, and it's discharging 80 liters per second to the main pipe. And right now we want to develop a greenfield site. Currently that greenfield is discharging about 20 liters into that main pipe, maybe through a table drain or something here. And the existing main pipe can carry about 120 liters per second capacity. So currently we're still well under, so that's fine. But now I'm gonna send a development application to council. I want to build a commercial center, for instance. And what happens if that is, that commercial center gets put in, you've got a whole bunch of roof, you got a bit of car park here, and then now you only have a bit of landscape. And what that does is it changes the amount that's being discharged to existing infrastructure, but also makes it so that it reaches the peak flow faster. So you get this phenomenon where you're discharging a whole lot into existing infrastructure, which is undersized. So how do we deal with that? As you can see, that's just not gonna fly. 120 versus 230 total, 150 from our proposed development plus existing. Definitely gonna flood something downstream. To deal with that, I guess easiest way would be to ensure that our development discharges at an existing rate. So that's an easy way to make sure that we don't have a no worsening condition, as some of you might commonly see in development conditions. Basically, it says that if you're going to develop any site, we should not make it worse for our neighbors or any downstream or upstream property owners, right? So one way to do that, we're gonna reduce that 150 back down to 20, which was the original. And typically this 20 liters per second is known as the permissible site discharge, or pre-development flows. But you'll notice if we're gonna reduce the discharge from 150 to 20, you have a excess flow. How do we store all this excess flow? That's where that on-site detention storage comes into play. So that's the whole reason why we're doing OSD. There might be other reasons. For example, maybe there's environmental flow benefits, so council might have some restrictions on the flows being discharged into creeks, things like that. But for the most part, it's about urbanization. We're developing more impervious areas. How do we handle the resulting increase in stormwater discharge appropriately to not cause flooding? All right, so now we've established the grounds for that. How do we know what flow is coming off our proposed development? Typically, most commonly we have the rational method, the good old rational method here, which basically says the flow, estimated flow from site, can be calculated based on the runoff coefficient, the rainfall intensity, multiplied by the catchment area, of course. And there's some unit conversion here, depending on if you want the flows to be output in liters per second or meters cubed per second or something like that. So let's look at the first parameter we need, catchment area. This one is typically you can just look at your drawings and you'll be able to figure that out quite easily. Sometimes we're doing studies on existing sites, and if we don't have any clear documentation or drawings on that, we can look at a lumped modeling, which basically says, if it's a residential area of medium density, we're going to assume runoff coefficients of 0.9. If it's a commercial zone, etc. This one down here, this is an example from the Victorian Infrastructure Design Manual. Different authorities or guidelines would have different recommendations, right? QUDM probably, Queensland Urban Drainage Manual has their own list of recommended coefficients. But the important thing to know is these coefficients can change depending on the council. Bringing us to the coefficients that can change, as we discussed, it's going to be based on your catchment or surface characteristics. Typically, the runoff coefficient will be low. For more pervious catchments or areas, think about landscape or rural residential areas where you have large lots, 1,000 square meters, but you only have like a dwelling of 200 square meters on site. And higher values of runoff coefficients typically associated with higher imperviousness. Like we discussed earlier, we're developing that commercial center, 80% roof and car park, you're going to get a lot of impervious areas. That is usually associated with a higher runoff coefficients. And to give you an idea, as we discussed, there are different ways to estimate this value depending on the authority. The IDM, as we showed you, is just a simple table. Pick out the corresponding catchment type or your land use, and you can get the recommended values. Queensland Urban Drainage Manual is more involved. Look up some tables, look up the intensities for the 10% AAP and so on. But this is just to give you an idea of how that runoff coefficient estimation does vary depending on where you're working. And of course, if we can justify our own coefficients, as long as we can justify it and council accepts it, that shouldn't be an issue. So we've looked at catchment, we've looked at the intensity. Last one would be we've looked at catchment and runoff coefficients. So the last one would be rainfall intensity. This is basically the rainfall on your site. So it's going to be based on your lat long, where you're working at, right? If you're working in Queensland, probably going to get higher values compared to SA. Important thing is we obtain the IFD data from the BOM website. And we need two additional variables in order to pick out a suitable rainfall intensity. The first one is the frequency. So over here you have an annual exceedance probability, which basically tells you what is the chance of that storm happening in any one year. This is typically outlined by the council requirements or your planning conditions. What you'll see is, councils would say, ensure no worsening on site for all storms up to 1%. So you'll probably be doing an analysis for 63.2, make sure there's no worsening, go up to 50, 20, 10, 5, 2%, and then 1. Or sometimes council might say limit all discharge from site to the 20% frequency, in which case you'll be doing the analysis for 20% on your PSD, for example. The duration, this would typically be determined based on your time of concentration. You can think of it as the time it takes for the entire catchment to contribute to your flow at the discharge point. And the most important thing here is you gotta do an analysis of the different potential flow paths of a drop of water can take, and the path that gives you the longest time would be the time of concentration. And then once you have the time of concentration, let's say for this project, time of concentration is 5, look at 5, and then council wants me to do assessment for 1%, so it's 5, 1%, I'm gonna use 187 millimeters per hour in my rational calculation. Another thing, recent change as well is for rainfall intensities. The Australian Rainfall and Runoff Book 1, Chapter 6 released a guidance, I think last year, on adjusting the intensities to account for climate change. This is based on the formulas they gave us, and it's related to the temperature change for each scenario. So they've given us a list of scenarios. Choose one that is relevant for your project, and that.
How do you choose this one, Greg, and how do you get the BOM information quickly?
Well, the BOM information quickly we can use our tools, but we'll do a couple of case studies at the end showing how to.
So it's good to know that that matrix is somewhat our invention, and increases in IFD generally depend on temperature.
Mm-hmm. Yeah. And over here, a brief, I guess a quick preview, you can see the differences in analysis for climate change. So if I'm just going to do a typical OSD project using the BOM 2016 IFDs for this site, I'm going to get 12.72 meters cube of storage. But if I'm looking at future scenarios, SSP 4.5, in 2080, I would need a 18.6 meters cube storage instead for this particular site layout. So that's a sensitivity analysis that you can do. Not sure how many councils are requesting for that, but of course it's based on the planning conditions, how sensitive is your site, and the discretion of either the council or the project owner. Noting that, of course, if we're accounting for climate change, we'll most likely have larger storage, which may or may not be good for the site. All right, so that's kind of a brief overview of the flow estimation. Now, once we got that done, how do we decide the size of our tanks? There's a couple of methods. One of the more, I guess, simpler or common ones, rational hydrograph method, basically says, okay, I'm going to assume flow increases linearly over time towards the peak flow at the time of concentration here. Right, so if you look at the shorter triangle, that's just my pre-development flows. It's going to go up all the way up to the point where my time of concentration is, where my site is contributing to where the entire site is contributing to the flow. And then it's just the storm is assumed to stop there, and then it slowly just trickles off as the remaining water flows towards the discharge point. So if we want to make sure there's no worsening, we're going to have to make sure that this peak discharges at essentially the same pattern as this line. So this is where that storage comes in. We're going to have to store the difference essentially, and that's just the formula right there. And the QO, QI, that's the flows, and that's why that rational formula we were discussing earlier, that's why it's important, because you're going to use that formula to get QO, right? So that's the pre and the post flows. You're going to put that into this formula, you're going to put in the time of concentration, and then you're going to just perform the calculation to get that storage volume that's required here. The modified rational, you can think of it as an extension of that previous triangle just now. You can see here that green triangle at the top, that's similar to the previous triangle, and that assumes the storm stops at the time of concentration and there's no more rain after that. But of course we know that's not always the case, right? You can have a time of concentration of 5 minutes, but then what happens if you have a 25-minute storm in that catchment? What does the discharge look like? So the way the modified rational works is you have that initial duration, and then you trial multiple factors. You basically multiply the time of concentration by a couple of factors, like so. So over here I got 2 times TC, 4 times TC, 6 times TC. I'm going to chuck that into the formula here. Q pre and Q peak, exactly like we did before. We're going to use rational method to calculate Qs. Once you chuck that into here, you're going to get a volume that's required for this green graph, and then you're going to get another volume that's required for the blue one, under the one that's required for the yellow one. And then you're gonna do that until you find the largest storage that's required, and that would be your on-site detention storage. And you'll notice this equation is essentially just calculating the difference between the areas above that red line. So if your Q-pre is here, then what is that volume above that red line? What is the volume above the red line in the yellow zone, in the blue zone, in the green zone? So that's what that formula is essentially estimating, just simple areas. Next one, Boyd's method. This is also a variation. You can see you're going to be iterating across a range of durations as well, just like the modified rational. Over here, we did it up to 180 minutes, and you can see we've obtained a maximum storage at the 20-minute duration, so that's the critical duration, and you've got a storage of 17 meters cubed required for this site. And then over here is just a detailed calculation to show you guys what's going on. It's essentially the same thing. You're gonna chuck the correct parameters into this Boyd's equation. So all the Q's, we're gonna be using rational method again to get all the Q's, which gives me my R. And then Boyd's essentially assumes a simplified relationship which says that the storage volume required divided by the inflow volume, which is the volume of the post-development storm that goes into that gets discharged, is going to be equal to that ratio between the differences in your flows, your Q's. So once you chuck that all into this formula, you're going to get a required storage volume like this, and then you're just going to repeat it again for a different T value, and again for a different T value, until you get a maximum, which in this case is 17.04. The next one is the Swinburne method. This one is a bit more involved in that it requests the estimation of the catchment time of concentration. So if you're building like a 2-lot dwelling, for example, the TC that you're going to be looking for is not actually the time of concentrations for your site. It's actually going to be the time of concentration that applies to the whole catchment. So if it's on a precinct scale, then you're going to have to get that time of concentration for that entire precinct or the entire catchment that your 2-lot dwelling sits in. And you can see over here, right? So the TC, if you look at this square, that's your site, right? So I've got my 2-lot dwelling. It sits in a 20-lot precinct or something like that. And the TC I'm looking for is not actually the time of concentration of my site to the drainage. It's actually the TC of the entire catchment. And so you guys can probably see that if you're doing development in urban areas, there would be cases where this kind of information is very hard to get, right? You're gonna have to invest a lot into those studies. And so what most Victorian councils have done is they have performed that kind of analysis. And so usually what we do in Victoria is you would either you probably contact the council engineer first to see, okay, council, my development is here, and council will probably give you an indication of that TC value and the TSO value. And then once you have those values, you just chuck it into the OSD equation, and you get an output. To give you an example, the Swinburne method has different PSD and storage calculations based on the work done by Phillips, and this resulted in 3 different formulas to estimate the OSD storage requirements. So down here, I'm giving you an example of how that formula looks like. Of course, this looks a bit more involved than that rational method, simple QCIA. This one has a more involved formula. And you're going to have one PSD formula for below ground pipe and the volume for below ground pipe, but if you're going to calculate above ground, you're going to be using a different formula, and that's all outlined in our tools, but also in the paper here if you want to read more on that. So to recap, Swinburne method is based on a catchment-wide TC, and some complications may arise from not having enough info, and you will need to contact council. And also, these equations are more involved, so you might have trouble calculating them if you don't have any appropriate tools. And that's why in Victoria there's a tool called OSD4W. It's a legacy software. It's no longer maintained. Things to note about this software in Victoria: it was used previously back when the 1987 IFD data was valid, so it did serve its function, helps us with performing the calculations. We don't have to create a complex Excel sheet to run all those formulas. Simple inputs spits out an output. But issue is 1987 IFD data, right? Now we're using 2016 IFD data. So that IFD data is outdated, and also because it's no longer maintained, we can't do any of that climate change analysis that we were talking about earlier. We can't do any of that in the OSD4 software. And also, if you're comparing the original equations developed by Phillips against the OSD4 software, there is a safety factor of 2 in the OSD4 software as well, just to be aware of when we're performing that analysis. So the next storage estimation method, I guess, is the runoff routing methods. These establish a more detailed relationship between flow and storage, but it does give us a better estimation of storage requirements because of that. So how that works, there's a runoff routing relationship between storage, and storage is a function of K and M parameters integrated with flow. And we can already see here, you would need way more inputs compared to the rational method. We need to consider temporal patterns, which is the variation of the storm across time. We noticed earlier in the rational method, the hydrograph is just simple straight line, up and down, but of course we know in reality storms are not just straight lines up and down, right? So that temporal variation is considered in the more complex runoff routing methods. Pre-bursts as well, catchment losses, and the routing parameters K and M, right? So we need to understand what values to apply for K and M. Routing parameter K, you can think of it as almost similar to the time of concentration. It tells you how fast the water gets discharged. The M parameter, I think the M parameter relates more towards the linearity of the drainage system or the river that you're modeling. I think a higher value of M, if M is 1, it's like a more straight line, straight pipe, and a lower value is more sinuous or curvy or complex, if you will. And this table right here shows you kind of the differences that we were talking about. This is pulled right out of the AR&R book. We'll put the link in the slides if you want to see more. But basically, multiple hydrology methods here, right? So rational methods, we've been talking about that earlier. Extended rational method and runoff routing. As we can see, runoff generation surface rational method is quite limited, but it has benefits in that it's a simple estimation method. You can do it. You can do a quick calculation and on the back of a notebook, things like that. It is also the basis of all. It's also the basis which all the other Boyd's, Swinburne methods estimate their flows. So it does enable the use of those methods. But you can see here, channel and storage routing in terms of estimation capabilities is not too great compared to the ones for runoff routing, like. As you can see here, ROR, BRAFs, WBNM, they're more in the moderate range, which is, I guess, more accuracy when it comes to estimating the on-site detention storage needs. But again, each method has its own merits, and most importantly, each method, depending on the council, may or may not be accepted, right? So again, depending on your region, you can or cannot use the rational method. Etc. So let's look at an example for that, right? So Melbourne City Council, they have a stormwater drainage design guidelines for and it talks about the OSD calculation requirements. So over here you can see if I'm doing a project in Melbourne City, how do I get my permissible site discharge? I'm going to have to use the rational method, right? Exactly like how we discussed. And we also discussed what frequency we should design for, and you can see here in the guidelines for Melbourne City, the PSD should be calculated as the runoff generated from pre-development site during a 20% AEP. So the frequency dictated by council for your PSD calculations should be 20%. So I'm going to use 20% here. For site storage, that's your OSD, right? Most importantly, council says it's calculated from post-development generated from a 100-year ARI. Well, this should be 1% AEP.
I mean, maybe, sometimes. It varies.
Well, I mean, yes. Ideally, they should, yeah. But over here, I'll be using the 1%, right? So as we discussed earlier, the frequency is typically dictated by what the council requirements are. And then over here, most importantly, it says calculations can be undertaken by applying voids, right? So we showed you guys the voids, but also you can use on-site detention for, as we discussed, OSD4W is a legacy tool for Swinburne method.
That doesn't use the IFD, the correct
yeah,
IFD, so we have that method.
Yeah. But this is again to show you guys that different authorities have different methods that's required for calculations, and it's always good to know and check before we go ahead with one method and then it turns out council is accepting a different one. And also, most importantly, right, see here it says where OSD4W is used, so Swinburne method, when Swinburne method is used, City of Melbourne's drainage engineer should be contacted to provide TC and TSO, just like we discussed earlier, right? Because the method is based on the entire catchment's time of concentration, not just your site, and it's typically difficult to perform that kind of analysis, especially if you're just doing a two-lot dwelling, right? So typically the councils in Victoria have been onto that kind of analysis, and we should be able to get the thing. So another requirement, this example is in Logan City. They're planning, as we discussed, no worsening. So you cannot flood downstream, ensure everything is equal or less than the pre-development situation. Most importantly here, it says does not result in adverse impacts for the full range of ARI storm events. So in this case, I'm not just looking at 20% and 1% like just now in Melbourne City. I'm looking at the full range, right? So 63, 50%, 20%, 10%. I'm going to have to do a report for each to figure out how to stage, how to design my stage discharge storage. Now for Logan as well, estimation of runoff volume. See, now it says use rainfall runoff modeling. So previously we saw rational method, voids, and Swinburne. Now in Logan we have, as we discussed, ROR. So the runoff modeling. Give me a second. Runoff routing software, right? So the more advanced one, where you have to consider K and M values, things like that. It does give you a note here. Says rational method can be used for relatively small scale catchments. Right, so even if councils do accept like do require the larger ones, some councils may give concessions. So that's why we're always saying it's important to, as you guys know, it's always important to see what's outlined in the conditions. Maybe if you can get away with the rational method, then you don't have to pay so much for a more advanced report. So those are a couple of examples. And lastly, the OSD storage types. Just show you guys what can be done. Rainwater tanks, a combination of OSD and reuse. Just make sure that when you see a 5 kiloliter tank, we make sure that we have appropriate volumes for detention and reuse specified. And those are the.
Let's go to an example.
Yep. So before the Q&A, let's look at a couple of examples where we can perform those kind of analysis, right? So to do that, you can follow along as well if you're online. But basically, in our website, you can just log in to the portal, and we're going to enter the project address. So let's see. We're going to try and do that Melbourne, Victoria.
Logan. Let's try Logan. You said about Logan. Oh no, it's ROR.
yeah, well, we can see the ROP one later, but
all right, we'll do our one later.
Yeah, but in Victoria, we'll look at that Swinburne one. So you click on OSD here once you enter your address. And we're going to have analysis like this. You can just close the pop-up.
Or read it first.
Mm-hmm.
Cool information.
Yes, I think that's about the climate change stuff. But yeah, so again, like we mentioned, a couple of methods. Make sure we know what method council is accepting. So if I'm going to do Swinburne, I'm going to call council. Council says 20%, 10%. Council says 12 for this.
How can you calculate it otherwise? Can you calculate it?
You can calculate it using the TC calculator here. And like we discussed earlier, right, when we were trying to estimate our time of concentration, we need to look at the different flow paths. So there's multiple methods to calculate that. These are all based on the Queensland Urban Drainage Manual. But of course, you know, if I have like a stop on length of flow path, let's just say 50. Again, it's all there's all like question marks to help you guys out.
Oh, what's that question mark? Length of flow path.
Just tells you the different assumed length of flow path.
Okay, yeah. Got you. And the other one, Hawthorne coefficient?
It just gives you the
all
coefficients that you can use to estimate the Hawthorne coefficient.
So what I understand is everything you told me before, it's all right, I don't have to search for the guidelines, I can just use this tool. And I know everything.
I would say pretty much. So like impervious areas, paved surface 0.015. And then I can just calculate that. They're going to give me 5.91, and then that's done.
Awesome.
So I can do that, or I can get those values from council for Swinburne, like we discussed.
Oh, and I see this is the OSD4W method. So it's Swinburne specific for OSD4W?
Yes, that's because earlier in the presentation we discussed these OSD4W has a safety factor of 2, so if you use the standard one, then it removes that. It's
a safety factor of 2, but only in the guts of the formula somewhere. It's not just a flat safety factor of 2.
Yeah.
It's somewhere in some hidden space.
Yeah, some parameter in the PSD, I believe. Yeah. But yeah, you can do like you can have a specified PSD here, for example, if council has provided it, and then all I have to do is my post development, and I've got my, let's say, my commercial area and my runoff coefficients.
What can it be?
Like we discussed, right? We have those tables from council, so you can.
Oh, it's 0.9 actually.
So, yep.
And then what does uncontrolled mean? Uncontrolled means in this story that?
Uncontrolled areas, we have that there for situations where you might have different areas of your site. You can't, let's say you have different areas of a site sloping in different direction. One sloping towards the backyard or the back of site, and the entire car park is sloping towards the front. Sometimes you can't control the whole area with your OSD tank, so you specify the
Alright, so that one is flowing uncontrolled. Mm-hmm. So it is, if that area is too big, means it's potentially impossible to achieve the pre-development targets.
That is correct.
So only a small uncontrolled area.
Yeah.
Maximum.
And some guidelines actually specify like a hard percentage on your site as well. I think.
Okay.
Yeah. So those are the parameters we discussed, and essentially I'll show you a real quick.
It's a way to validate that what we do in OSD4W is the same?
Yeah, but yeah.
All right, that's more Victoria specific and more into detail. So
yeah, so
the information is there, guys. If you want to, you can watch the video if you want to verify that OSD4W and our analysis provides the same result. And that's a orifice calculation. Oh, cool.
Yeah. So as we
question mark
with the orifice calculation, it's just a simple orifice formula over there. It's optional, of course, so you can use your own if you want. And then just as we discussed, there's multiple storage types. For Swinburne, it matters, right? Because we have those different formulas for each storage. So I'm going to just pick a typical rainwater tank, for example. It's going to give you the calculations. Of course, you can do it on, yeah, like so. So you see in Swinburne, if you're doing an above ground storage, you need 17.15, below ground pipe 19, and below ground tank is 20.8.
If you have a mixed one, you can run multiple calculations, but maybe just I don't know, either ratio it and just take the biggest value.
Yeah, it's like plus difference, not that much different, but yeah.
Yeah. All right, and there's a report there. Did that generate a report?
Yes. So that does generate a report. Typically, when you're doing all these calculations, the council would of course want those intermediate values, right? Okay. Just for assessment. That's so we can get the report and submit it to council, or you can just make your own report. Yes. So the report gives you all the information. These are essentially the same thing that we discussed in the presentation. So council knows what's going on. Gives you all the values, tells you if you've used any climate change adjustments or not. Gives you the formula that was used, standard drawings, and of course the calculations that we used to find the maximum volume.
How about modified rational?
Modified would be
that.
This one. This one is the...
What's the question marks doing there?
This one's letting us know what the pre-development frequency should be. As we discussed, this is based on the requirements of council. I think just now in Melbourne City, council says for your pre-development use 20, right? So we're going to do 20. Post-def use 1%, just like that. The storm durations, in Melbourne City, they say do investigations up to 2 hours. So if it's 2 hours, I'm just going to do some arithmetic here that would get me 2 hours.
So just step size, make the step size 2, please.
Okay, yeah, step size 2.
2 hours is
60.
120. Okay, yeah, done.
Yeah,
that's fine.
So that's going to give you 2 hours worth of calculations. And pre-development areas, you can put in let's say our existing greenfield. Again, 1,500. Like we discussed, we can calculate it, or we can just put in a value.
And what's the imperviousness? What's the question mark saying?
Imperviousness, this was what we discussed with the different guidelines. So IDM has infrastructure manual Victoria has their own table where you select a value, and then Queensland Urban Drainage has a different method.
So we can either use IDM or we can either use
QDOM. So if you want to use Queensland Urban Drainage,
you just call it impervious or pervious.
Yep. And then if you're in Victoria IDM, just define it here. Or if there's a different guideline with a separate set of tables, just use the user define, and then you put that in.
Perfect.
And that's it.
And the post-development?
You do the same thing for the post-development. You can calculate
What's TCU?
That's the time of concentration for the uncontrolled areas.
For the uncontrolled areas.
So if you have uncontrolled, you can run that.
Maybe we should swap it that way, because uncontrolled on top of uncontrolled makes me feel funny. We'll see. Let's see that.
Yeah, but we can definitely do that.
No.
Proposed development.
Oh no, it's good. Area is left, uncontrolled is right. No, it's fair. It's fair. Sorry.
1,500 again.
That's impervious for sure. Yeah.
Yeah, and then we can user define. I think IDM uses 0.95, I believe.
So let's run it.
Yep. So again, select your tank type. Maybe we're doing pipes. If we're doing pipes, again, do the same thing, and you'll get a result here.
Ooh, look at that.
And again, as we discussed, modified rational, you're going to have to find the biggest storage by iterating over the time, and we did so in up to 2 hours.
125
Should
minutes.
we report it?
Yeah, why not?
Okay.
Can
Let's
be
report
reported.
it.
Everything is reported.
Yeah.
And this is I guess, the advantage of using this kind of automated tool. So let me confirm. The intensity frequency duration data is picked like from BOM on the lat long here, right?
Yes, that's correct.
So
And
that one right there is based on that latitude and longitude. So I don't have to even worry. I just click on the map and all that data is generated.
I mean, if you do worry, you can copy the lat long here and put it into BOM and.
Okay. How about if I want the climate change to happen? Some climate change to happen.
Select that option there and
2050 for SSP
specify
2.5. Sorry, 2-4.5. 2050, 1.7 degrees heating.
Yep.
This one.
And
oh, look at that.
That's loaded up.
All right. So is it still? Can I still calculate?
Yep. So once you change that, it's going to ask you to calculate again because obviously you've made an update.
The data have changed. So I don't have to upload the IFD, download the IFD, use an Excel on the IFD, with all sorts of things like that. No.
No. I mean you can, but why? Why would you?
Fair enough. Right. So let's see what the report says now. I think now we're at a higher number of minutes, and the numbers are different.
Yeah, because we adjusted the
the
climate change.
post, yeah.
So we're gonna re-download the climate change report. I guess over here now we can compare the climate change, how the climate change report looks like.
Yeah.
Yeah. So again, gives you all the details like we discussed, intermediate values, critical durations as well. As we discussed, all the method. Where is it?
Did it accept the climate change? Oh.
Climate change for post.
Oh, it's not climate change because we didn't do it in the beginning, so you can't do the resets like that.
Yeah.
It will be fixed.
Yeah.
You can go back to it. Where is it? So we have to rechange the values now, or reload the image, reload the page. But it's okay. Good to know.
Yeah.
Don't do it without and do it with. Do it with from the beginning.
With climate change from the beginning?
Yeah.
Okay. 1.7. Wait, no, it's the modified one. 1.7. We'll speed this up and give it 10.
Yeah.
And we'll do 6 post dev.
1500. Oh, that's a lot. 0.8. That's fine. Let's see what it says now.
Oh wait, we were using pipes, I believe.
Alright. Random pipes.
And
Anyways, the report should say the climate change that's happening and everything. So the report will have all the information. Ooh, look at that. Oh, because of the steps, because we had the default steps.
default steps, but also
3 hours.
we calculated the PSD previously, but now we specified
now
10.
we have not.
Yes.
So it's a different PSD.
Yeah.
All right. So this should tell you all the climate change information.
It should. So
You better do it.
yeah.
Delta temperature, 1.7 degrees, rate of change 15.
Yeah.
So this is the climate change one.
Mm-hmm.
We'll fix that error so you can run the climate change anytime.
And yeah, all our reports have all the method and the storage calculations there. So yeah, it's easy for council to see what's going on, and such. So yeah, so there's a couple of I guess case studies and applications where you can calculate or estimate your on-site detention and your discharge requirements for each site. Most importantly, of course, each development is unique depending on the planning or development conditions imposed, where you're working in. If you're working in Queensland, you're probably mostly referring to the QU, Queensland Urban Drainage Manual, for guidance on these calculations. If you're in Victoria, probably IDM. Or if councils have their own guidelines, that's the one we should go for.
What's the Q&A?
The Q&A? Chat.
No, it's a specific Q&A.
Oh, there's a Q&A thing.
Wait.
Where is it? All right, cool.
So are we close to Q&A?
Yeah, I think, we have about, just on the dot actually, we got about 15-ish minutes.
Right, so Max asked, for a large project,
Mm-hmm.
the design discharge location might not be the same as the original waterway. Then the total catchment would be different for different waterways. In this case, how to match the permissible site discharge, use the post-development total catchment to estimate PSD, or use the PSD of the pre-development at the design discharge. How to determine if OSD is required for development in rural area. All right, so there's two questions here. One of them is, let's say you have a really big catchment, and this catchment, half of it, or like, let's say, okay, a third of it flows to Creek A, and maybe 2/3, 67% flows to Creek B.
Mm-hmm.
But then when you build the whole site, more will go to Creek A. Let's say developed, maybe 60% will go to Creek A,
Mm-hmm.
and only 40% to Creek B. So this situation happens a lot, and a lot of times this is potentially a negotiation with council or the authority responsible. But typically what you don't want to do is you don't want to oversize, like you don't want to be too high on the peak discharge. So then what you would genuinely do is calculate your permissible site discharge for your pre, and then maintain that for your post. So you have to do a couple of funny things, because obviously the areas are not gonna match. So what you're gonna do is you're gonna try to figure out the curve of your pre, depending on the times of construction and all that, and you're gonna then run the curve on your post, and you'll separate them kind of manually. We could implement this type of calculation in, however, it might be a little bit difficult from a user perspective, to figure out what's happening. But I think we can. I think we can have another method that says different, or another checkbox that says pre and post is different. But typically, you would have, if they go different locations, the pre and post area would not match. The post area would be bigger or smaller than the pre. So then you are making sure that whatever the peaks from the pre are not overtaken by are not worse than the peaks from the post.
Mm-hmm.
With rational method is probably easiest. You get the maximum the peak flow, and then you just put it at PSD.
Mm.
Or even all the other methods. You can just calculate the PSD with the rational, or with any method, not apart from swim, but swim will be different.
I think also for rational method, if the project gets a bit large, like some councils also have limitations on the areas.
Yes,
so
they do.
If
some authorities have limitations.
Mm-hmm.
But like, if it's there where you can use it, yes. Set the pre, calculate the pre flow, and then maximum flow in the pre-state, and then just put it in as a permissible site discharge. Mm-hmm. And that's it. Now, RORB, do we have some way to calculate with RORB?
Yeah, so if, let's say we're doing that Logan project where council needs RORB, we can do that as well. That would be the same. You enter, let's go to Logan, for example. Logan, Queensland. Quite sunny there now, I believe.
It's always sunny.
Mm-hmm. So for that RORB calculation or the runoff routing, we're going to go to super hydrologic over here. And as we discussed, let's select RORB, for example. And we're going to just set up our site. So if we're doing a carport, we have to know the effective impervious areas, for example. Let's do that 1,500 like we did.
We probably don't have time to describe very well, but this is a way to create raw models. We feel it's far easier and faster. It finds the little rainfall cloud. It finds the IFD data and all the information automatically. You don't have to go to BOM or ARNR website. It's just all pulled down automatically. And then you also have a button for council rules. Do we have any council rules in here? Maybe.
This occasion,
No,
not yet for
OSD.
Yeah.
Yeah, not for OSD. All right. So then you can just create your storage, custom tanks, detention basin, underground tanks. So all of this is available right now, and raw model can be done and run. But that's a little bit more advanced. Just to know that there's some modeling also that does not necessarily, I mean, it's considered to be more advanced than the models that we have shown. However, it's important to know that sometimes the authority requires that the models are calibrated back to the rational methods. I'm not really sure. It happens. It happens often.
Yeah, we can probably run a separate.
We'll run a separate webinar on ROAR.
But like we discussed in the presentation, there's more parameters, K and M. How do we know what values these are? There's a bunch of guidance on that, but yeah.
So the question marks really hopefully tell you everything you need to know, and hopefully graduates that haven't had almost any experience in the field, you don't need to go to Bureau of Meteorology, you don't need to go to ARNR, you don't need to create your own Excel for climate change analysis. It's simply, if we look at climate change, all of it is there on OSDs for VIPs. All of it is there. You can actually run a pre-development climate change data set as well. Just click on that.
Yep.
And then you can see what's the difference between now and climate change, and what's the difference between climate change and climate change, or climate change and now, whatever. I mean, there's a bunch of options and types of analyses. No, analysis. Types of way to analyze this.
Yep.
So that's the first question. And the second question is the OSD is likely required for development in rural area. Just a calculation of, well, are we increasing the outflows from here or not? If we're increasing the peak flows, then definitely it's important to have some storage. Now we have another question. What's the pricing arrangement for the software? This software is mostly free. There's if you run a calculation, you have to pay, I think, 7 cents.
Yeah.
But you get 10 cents gift when you create an account, so it will allow you to run many calculations.
Not 10 cents gift, $10.
Sorry, $10 gift. Yes, correct me on that. So it would be 100 and something calculations for free. With the climate change for free. I'm sure it saves a lot of time. Simply going to the Bureau of Meteorology or trying to run the climate change for the information would be taking a decent amount of time. Definitely more than charge out rate for 7 cents. So that's the pricing arrangements and the reports, which we feel are quite comprehensive. They cost, a report will cost about $25, and it's quite, it says there how much, and it's we feel quite useful instead of just writing the report by hand or putting the values in by hand. That's still quite a lot of time. And if I'm not mistaken, our climate change data sets can be actually, you can download the report about it and with all the information. And we have, in the report is information here. In the report, the climate change information is here. But also you can download the specific climate change report information from Stormwater. Stormwater design tools. So that's a different, if you go to the portal, that's a different software, and it allows Stormwater design tools, and it allows you to do climate change and download the report for that specific climate change information. A more comprehensive report, if you wish to do so. Yeah, so that was, hopefully that answered the question about price arrangement. Always you can recharge. So there's a, how do you recharge, Greg? You go to the account or where, recharge $10, and you can recharge, and there's a price list that shows all the costs. It's pay per use, so pay very little per use. So it's very, very cost effective, we feel. That was the other question.
Mm-hmm.
Any more Q&A?
Let me scroll.
No. All right.
Yep.
Well, unless you guys have any other questions, very happy to thank you for attending our webinar, and good job, Greg. I loved it. And let us know if you have any questions, and we'll send everybody the presentation after.
Yeah. Yeah, and if anyone wants the CPE search, just send us a message. And
Send us a message. Absolutely.
Yeah.
Thank you very much.
Thank you. Have a good one.
Ooh, there's a message in chat. An event.
I think that message was the AI.
Oh, some AI told us something.